class, welcome to another episode of The Professor. Last video we talked about probabilities and what this and what not, and today we'll be focusing on belief networks or the Bayesian network. So the Bayesian belief network or Bayesian network or belief network is a probabilistic graphical model that represents conditional dependencies between random variables through a directed acyclic graph, or which we commonly know as the DAG. So in other words, it's a graph. It's a graph that shows connections between one node to another, and the graph has to be a DAG. A DAG meaning that there are no nodes that connect to other nodes and later would eventually connect back to itself. The Bayesian network is used in a lot of ways. One would be to detect the disease based and given on the symptoms, or determining why a grass is wet given the weather. And to compute the probability, we need this specific formula. So to compute the probability of a random variable, we have to compute the probabilities of its parent variable. Now, to give us more context, before that, this is what a graph with a cycle looks like, and this is what a graph that is a DAG. So if you can see, the graph with cycles has directed edges that goes back to itself, while directed acyclic graphs do not. Now, to give us more context and to help us understand further what the Bayesian network is, we have a sample graph here. We took this example from a video of a YouTuber called Subalitha CN. So here we have 5 nodes: windy, cloudy, rain, wet grass, and do not go to work. And we have truth tables. All these are given, right? So our task is to compute the probability of a wet grass. For us to be able to do that, we have to get the probability of the wet grass given that it will rain, multiplied with the probability of rain, plus the probability of the wet grass given that will not rain, multiplied with the probability that it will not rain. But given our graph, we only know the probability of wet grass given that it will rain, which is 0.9, and the probability of wet grass given that it will not rain, which is 0.05. The probability of rain and the probability of not rain remains unknown. So now we have to get the probability of rain. For us to be able to do this, going back to our graph, we have to get the probability of rain given that it's windy and cloudy. If we check our graph, the probability of rain that it's windy, true, and cloudy, true, is 0.95. That's why we have a 0.95 over here, times the joint probability of windy and cloudy. Go back once again. To be able to get the joint probability, we just get the products of the probability of the variables. So to get the joint probability of windy and cloudy, we multiply 0.001 to 0.002. That's what we have here. Plus the probability of rain. So we're basically taking all the possible scenarios here, right? So next, we get the probability of rain when it's not windy, but it's cloudy. So the probability of rain when it's not windy, false, but it's cloudy, that's 0.29. So that's why we have 0.29 over here, right? Times the joint probability of not windy and cloudy. Now remember once again, how do we get the probability of not windy? We just have to subtract the probability of windy minus 1. So 1 minus the probability of windy, we get the probability of not windy. So that's why we have 0.999 times the probability of cloudy, which remains 0.002. So we continue this process after we get all of the values. If we already checked everything in the truth table, and then we'll have this value. So the probability of rain is 0.00252 or 0.003%. Next, there's another unknown variable, which is the probability of not rain. To be able to get that, there's only one slight difference. We just have to subtract the probability of rain given windy and cloudy, the probability of rain given not windy and cloudy, the probability of rain given windy and not cloudy, and the probability of rain given not windy and not cloudy. So if you just notice, it's the same formula from before, but we just added a 1 minus that probability. Because to be able to get the probability of rain opposite to this, we just subtract 1 from this, right? So that's what we did, and then we got the value of 0.9974 or 99.7%. Now we have the probability of rain and the probability of not rain. We can now proceed with our equation to compute the probability of a wet grass. So we have 0.9 times 0.00252 plus 0.05 times 0.9974. We get a probability of 0.0052138, or the probability of a wet grass given our Bayesian network is 5.21%. Moving forward, we have probabilistic inference. So probabilistic inference is the task of inferring an insight from a graph. So meaning this is the time where we get the answers from the graph, right? So there are two approaches to probabilistic inference. We have exact inference and approximate inference. Now for exact inference, we have a process called variable elimination, where from the name itself, we only have to eliminate all the other variables once we have the only variable that we're concerned of. Take for example this situation where we have three nodes A, B, and C, where node A is pass major subject, node B is graduate from college, and node C is take master's scores. Now in this example, what we're concerned of is to compute the prior marginal on variable C. Therefore, in able to achieve this, we have to eliminate all the other variables A and B. And to do that, let's start eliminating variable A. To be able to eliminate variable A, we have to look at the factors wherein A belongs. When I say factor, one truth table is equivalent to one factor. So in here, in this example, we have three factors, and we have to look at the factors where A is present. That would be the factor theta A and theta B given A. Next is that we multiply these factors first and then sum out variable A. So how do we multiply two factors? It's basically just a simple process. We take the value where A is true. The probability that A is true is 0.6, and multiply it to the probability of theta B given A, considering that A is true, which in this case, the first two rows. So since A true is 0.6, multiplied by this row, since A here is true, 0.6 times 0.9, we have 0.54. Going back, 0.6, since A is true here again, we multiply 0.6 with 0.1, we get 0.06. Now to continue this process, we now multiply the value of probability that A is false to theta BA, where A is also false. So 0.4 we multiply with 0.2, and 0.4 we multiply with 0.8, where we get 0.08 and 0.32 respectively. Now that we are done multiplying, the next step is now to sum out variable A from the resulting factor. In order to do that, we have to put our focus on the B column. And then we add both of the true instances of B, which is the remaining variable, which is 0.54 and 0.08. Now we have 0.62, and add both of the false instances where we have 0.06 probability plus 0.32 probability. That will lead us to 0.38. So now we have summed out variable A and we have variable B, which remained with a true probability value of 0.62 and a false probability value of 0.38. So now we are left with factor A multiplied by B given A, and then theta C given B. So we repeat the same process. We multiply this factor to this factor to hopefully sum out B and eliminate B. So we have 0.62 true times 0.3, because B here is true. We get 0.186. So we look again on another instance where B is true. So 0.62 times 0.7, and then do the same to false. Since B is false, we look at an instance where B is false in this table, which is this. So false value is 0.38 times 0.5, and the same way 0.38 times 0.5, and then we get this final value. So now we have this. We now have to sum out B, and to do that, we ignore B and focus on column C and add both of the true instances as well as both of the false instances. So we add 0.186 to 0.190, we get 0.376, and we add 0.434 to 0.190, we get 0.624. So now we have the marginal probability of C, which is 37.6% true and 62.4% false. And as you notice, if you add both values, we get 1, which is what we expected. So this is how this process works. Variable elimination works. We just have to eliminate one variable from another until we have the variable we're concerned of left. So now we have approximate inference, or the stochastic simulation. Stochastic simulation is a simulation of a system that has variables that can change stochastically or randomly with individual probabilities. These changes are then inserted back into the model for us to be able to draw a new type of inference given the changes in the values. So one example of this is the Monte Carlo simulation, where there was one instance where we create a stochastic model where through it we can simulate how a stock market portfolio will perform based on the probability distributions of individual stock returns. So the stock market is a perfect example for this example of inference, because as we all know, variables in the stock market or the stock prices can change from time to time. It can go up and it can go down, and there are individual probabilities where we can compare this to the individual stock prices. So that's all for this video, and for the next video we'll be focusing on Markov chains and sequence probability models. Thank you.